I have a very difficult task. I'm a spectroscopist, and I have to talk about astronomy without showing you any single image of nebulae or galaxies, etc. Because my job is spectroscopy. I never deal with images. But I'll try to convince you that spectroscopy is actually something which can change this world. Spectroscopy can probably answer the question, is there anybody out there? Are we alone? SETI. It's not very fun to do spectroscopy. One of my colleagues in Bulgaria, Neviana Markova, spent about 20 years studying these profiles. And she published 42 articles just dedicated to this object. Can you imagine day and night thinking, observing the same star for 20 years is incredible. But we are crazy, we do these things. And I'm not that far. I spent about 8 months working on these profiles because I've noticed a very small asymmetry in the profile of one of the planet host stars, and I thought, well, maybe there is lithium-6 in this star, which is an indication that this star has swallowed a planet, because apparently you can't have this fragile isotope of lithium-6 in the atmospheres of sun-like stars, but you have it in planets and asteroids. So if you engulf a planet or a large number of asteroids, you will have this lithium-6 isotope in the spectrum of the star. So I invested more than 8 months just studying the profile of this star. And actually, it's amazing because I've phone calls from many reporters asking, have you actually seen the planet going into a star? Because they thought that if you are in a telescope, you are an astronomer, so what you are doing is actually looking in a telescope, and you might have seen the planet going into a star. And I was saying, no, excuse me, well, what I see is this one. It's just incredible because nobody understood really. I bet that there were very few people who really understood what I'm talking about, because this is the indication that the planet went into the star. It's amazing. Well, the power of spectroscopy was actually realized by Pink Floyd already in 1973. Because they actually said that you can get any color you like in a spectrum, and all you need is time and money to make your spectrograph. It's a #1 higher resolution, most precise spectrograph on this planet called HARPS, which is actually used to detect extrasolar planets and sound waves in the atmospheres of stars. How we get spectra, I'm sure most of you know from school physics that it's basically splitting a white light into colors. And if you have a liquid hot mass, it will produce something which we call continuous spectrum. A hot gas is producing emission lines only, no continuum. And if you place a cool gas in front of a hot source, you will see a certain pattern which we call absorption lines, which is used actually to identify chemical elements in a cool matter, which is absorbing exactly at those frequencies. Now, what we can do with the spectra, we can actually study line-of-sight velocities of cosmic objects, and we can also study chemical composition and physical parameters of stars, galaxies, nebulae. A star is the most simple object. In the core, we have thermonuclear reactions going on, creating chemical elements, and we have a cool atmosphere. It's cool for me. Cool in my terms is 3,000, 4,000, 5,000 degrees. My colleagues in infrared astronomy call -200 Kelvin is cool for them. But you know, everything is relative. So for me, 5,000 degrees is pretty cool. This is the spectrum of the sun. 24,000 spectral lines, and about 15% of these lines is not yet identified. It is amazing. So we are in the 21st century, and we still cannot properly understand the spectrum of the sun. Sometimes we have to deal with just one tiny weak spectral line, to measure the composition of that chemical element in the atmosphere. For instance, you see the spectral line of the gold is the only spectral line in the spectrum of the sun. And we use this weak feature to measure the composition of gold in the atmosphere of the sun. And now, this is a work in progress. We have been dealing with a similarly very weak feature, which belongs to osmium. It's a heavy element produced in thermonuclear explosions of supernovae. It's the only place where you can produce actually osmium. Just comparing the composition of osmium in one of the planet host stars, we want to understand why there is so much of this element. And perhaps we even think that maybe supernovae explosions trigger formation of planets and stars. Can be an indication. The other day, my colleague from Berkeley, Gibor Basri, emailed me a very interesting spectrum asking me, well, can you have a look at this? And I couldn't sleep next 2 weeks. When I saw the huge amount of oxygen and alpha elements in the spectrum of these stars, I knew that there is nothing like that observed in the galaxy. It was incredible. The only conclusion we could make from this is clear evidence that there was a supernova explosion in this system which polluted the atmosphere of this star, and later a black hole was formed in a binary system, which is still there with a mass about 5 solar masses. This was considered as the first evidence that actually black holes come from supernovae explosions. My colleagues, comparing composition of chemical elements in different galactic stars, actually discovered alien stars in our galaxy. It's amazing that you can go so far simply studying the chemical composition of stars. They actually said that one of the stars you see in this spectra is an alien. It comes from a different galaxy. There is interaction of galaxies, we know this, and sometimes they just capture stars. You've heard about solar flares. We were very surprised to discover a super flare, a flare which is thousands or millions of times more powerful than those we see in the sun. In one of the binary stars in our galaxy called FH Leo, we discovered a super flare, and later we went to study the spectra of stars to see is there anything strange with these objects, and we found that everything is normal. These stars are normal like the sun, age, everything was normal. So this is a mystery. It's one of the mysteries we still have, super flares, and there are 6 or 7 similar cases reported in the literature. Now, to go ahead with this, we really need to understand the chemical evolution of the universe. It's very complicated. I don't really want you to try to understand what is here, but it's to show you how complicated is the whole story of production of chemical elements. You have 2 channels via massive stars and low mass stars producing and recycling matter and chemical elements in the universe. And doing this for 14 billion years, we end up with this picture, which is a very important graph showing a relative abundances of chemical elements in sun-like stars and in the interstellar medium. So, which means that it's really impossible to find an object where you find about 10 times more sulfur than silicon, 5 times more calcium than oxygen. It's just impossible. And if you find one, I would say that this is something related to SETI, because naturally you can't do it. Doppler effect is something very important from a fundamental physics. And this is related to the change of the frequency of a moving source. The Doppler effect is used to discover extrasolar planets. The precision which we need to discover a Jupiter-like planet around the Sun-like star is something like 28.4 meters per second. And we need 9 centimeters per second to detect an Earth-like planet. This can be done with the future spectrographs. I myself, I'm actually involved in a team which is developing a codex, high-resolution future generation spectrograph for a 42-meter ELT telescope. And this is going to be an instrument to detect Earth-like planets around Sun-like stars. It is an amazing tool called astroseismology, where we can detect sound waves in the atmospheres of stars. This is sound of an alpha sen. We can detect sound waves in the atmospheres of Sun-like stars. Those waves have frequencies in infrasound domain. These are actually not in audio domain. Coming back to the most important question, is there anybody out there? This is closely related to tectonic and volcanic activity of planets. The connection between life and radioactive nuclei is straightforward. No life without tectonic activity, without volcanic activity. And we know very well that geothermal energy is mostly produced by a decay of uranium, thorium, and potassium. How to measure? If we have planets where the amount of those elements is small, so those planets are tectonically dead, there cannot be life. If there is too much uranium or potassium or thorium, probably, again, there would be no life, because you can imagine everything boiling and there's too much energy on a planet. Now, we have been measuring abundance of thorium in one of the stars with extrasolar planets. It's exactly the same game, a very tiny future. We are actually trying to measure this profile and to detect thorium. It's very tough. It's very tough. And first you have to convince yourself. Then you have to convince your colleagues. And then you have to convince the whole world that you have actually detected something like this in the atmosphere of an extrasolar planet, host star somewhere in 100 parsec away from here. It's really difficult. But if you want to know about a life on extrasolar planets, you have to do this job, because you have to know how much of radioactive element you have in those systems. The one way to discover about aliens is to tune your radio telescope and listen to the signals. If you receive something interesting, and well, that's what SETI does actually, that's what SETI has been doing for many years. I think is the most promising way is to go for biomarkers. You can see the spectrum of the Earth is the Earthshine spectrum, and there is a very clear signal. This slope which is coming, which we call a red H, is a detection of vegetated area. It's amazing so that we can detect vegetation from a spectrum. Now imagine doing this test for other planets. Now very recently, I'm talking about last 6, 7, 8 months, water, methane, carbon dioxide have been detected in the spectrum of a planet outside the solar system. It's amazing. So this is the power of spectroscopy. You can actually go and detect and study a chemical composition of planets far, far, far from the solar system. We have to detect oxygen or ozone to make sure that we have all necessary conditions to have life. Cosmic miracles are something which can be related to SETI. Now imagine an object, amazing object, or something which we cannot explain when we just stand up and say, look, we give up. Physics doesn't work. So that's something which you can always refer to SETI and say, well, somebody must be doing this somehow. And with the known physics, etc., it's something actually which has been pointed out by Frank Drake many years ago on Shklovsky. If you see in the spectrum of a planet host star, if you see strange chemical elements, it can be a signal from a civilization which is there, and they want to signal about it. They want to actually to signal their presence through these spectral lines in the spectrum of a star in different ways. There can be different ways doing this. One is, for instance, technetium is a radioactive element with a decay time about 4.2 million years. If you suddenly observe technetium in a sun-like star, you can be sure that somebody has put this element in the atmosphere, because in a natural way it is impossible to do this. Now, we are reviewing the spectra of about 300 stars with extrasolar planets. And we are doing this job since 2000. And it's a very heavy project. We have been working very hard, and we have some interesting cases, candidates, so things which we can't really explain. And I hope in the near future we can confirm this. So the main question, are we alone? I think it will not come from UFOs. It will not come from radio signals. I think it will come from a spectrum like this. This is a spectrum of a planet like Earth showing a presence of nitrogen dioxide is a clear signal of life and oxygen and ozone. If one day, and I think it will be within 15 years from now or 20 years, if we discover a spectrum like this, we can be sure that there is life on that planet. In about 5 years, we will discover planets like Earth around sun-like stars, the same distance as the Earth from the sun. It will take about 5 years. And then we will need another 10, 15 years with space projects to get spectra of Earth-like planets like the one I showed you. And if we see the nitrogen dioxide and oxygen, I think we have the perfect ET. Thank you very much.